Good afternoon, Professor Wen, and welcome to our demo for the presentation of job share secure cloud file sharing. Uh,
I'm here and I handle the front-end development, and my partner Chung handle the advanced back-end architecture. So let's dive into what we build. So what is the drop share? Drop share is a platform designed to let users share file quickly and securely. And when you upload a file, it's an instant uh, shareable link, and you can set custom limits like how many times it can be downloaded and exactly when the link expires. For the user interface, I built a React single-page application using Vue.js.
and on my back-end side, I engineered a REST API using the ASP.NET.Core 9. And because cloud platform like Render doesn't have a local file safe only, so we connected API to the Cardinally to access our media storage CMD. And we use relational database, which is PostgreSQL, to keep track of all the file metadata and the expiration limit.
And to bring it all to life, both the front-end and back-end are hosted like on the Render cloud platform. So let's into the high-level system architecture. And this is diagram show our high-level architecture. We will celebrate our concerts. The user interacts with the Vue.js frontend in their browser. Whenever they do something, the frontend communicates with the backend through REST API call using assert.
And once the request hit the AWS.NET Core backend, the server acts as like a orchestrator. Is the most important part of our architecture. The heavy file payload bypass our application server local storage entirely, so the backend will stream the file directly to our cloud ordinary and only save the lightweight metadata like the download count and the shortcode into our database, which is the PostgreSQL, to keep our API incredibly fast and scalable.
So let's into the front-end interface and cost base. Uh, Looking closer at the front end, we focus on the smooth user experience. We use Vise as our build tool because uh, build tool because it gives us a fast update during development and optimize our code for production. And the UI is built using reusable and modular view component style with Tailwind CSS to make sure communication with the backend is stable. We set up ASIC interceptors. This means if there is an error like an expire link or a network issue, the interceptor catches it and show a friendly message to the user instead of breaking the app.
And moving on to the file upload workflow, which came from the backend, and the is what exactly happen when a user drop a file into our app, which is the front-end viewer. The viewer front-end will send a custom send the file and the user custom limit to our API, which is the ASP.NET Core. Instead of saving the file to the local disk, the API open a stream and send it to our cloudinary. The cloudinary give back the secure SQL. We then give it the SQL back to the alongside the expiration date, the download limit, and the generated shortcode into our database, which was SQL. Then finally we confirm save back into our API and send back the 201 create 201 created status back to the our UI frontend with a shareable link for the user.
And next to the GitHub repository and CI/CD pipelines. For our DevOps strategies, we decided to keep things completely separate. We had two distinct GitHub repositories, one of the frontend and one of the backend. Each repository has a custom Docker file because they are separate and set up to independent GitHub action CI/CD pipelines. This means when I update the front-end UI, when I put and commit and put the new code to the GitHub, and it will automatically test and deploy to render without integrating from backend API.
And onto the secure download and redirect workflow. When a user share a link, we have a straight validation process. So first, the client gets the file by short code, the authorization token. Second, the backend queries will check the policy from the database. We check if the timestamp the file has been expired yet, or how many count has it done, if it hasn't been reached yet. If it has, then we will return a 410 error gone. But if it's a bad one, we move on to the step 3, which is an automatic update to our PostgreSQL to download counter. Then we move on. Finally is a step 4, which issues the 302 redirect. So it sends the user browser directly to the connected asset. This means that the download doesn't slow down our API server. For the automated backend cleanup, this is also the backend. So the big problem I see when I use my file sharing platform is that link and the stale data would pile up and bloat my database, which was PostgreSQL, and leaving dangling cloud assets in both the render and the cloudinary. So one came up with a solution is that I built a file cleanup service, JS, CS, my bad. It's an dedicated automatic backend worker built into the APS.NET Core backend. Run a periodic script without any manual intervention. The core execution logic is that it will check for the expiry, identify which file whose custom expire at has been passed or not, the threshold check, if the check file hasn't hit the allowed download maximum count yet, then it will, if all is hit, it will do a do purge. It will actually automatically strip the record from the PostgreSQL database and then delete the asset from the cloud. Ordinary awesome. The result then ensure the optimal storage management and return a clean 410 gone status for any attempt if they use the shareable link for the deleted file again.
So to presently have a reliable referral automated test for both sides. For the front end, I use write test and heavy down, and they simulate a browser environment, so I can for simulate a browser environment for verification component and what and utility function component so what we take utility function component rendering and interactive UI stage, API integration and errors handling using Azure mocks.
And for my background testing, I use XUnit because we were using the repository pattern. I was able to mock the database itself, so I could write tests to verify control the routing logic and the response statuses, the file metadata validation rules, the expiration check, and the download count. And the lastly is the integration logic between the repository and the background cleanup. So on to the last slide. We will talk about how we conquer the technical bottleneck. There are three major challenges we face, which was the ephemeral local storage. The problem at first was the cloud hosting storage like vendor wipe off our local container data when we start. So when we auto deploy from the Docker Hub, it would wipe the data completely, causing the upload file to disappear. The solution I came up with was integrating the Cardinally to store the media and design the backend to stream multiple platform data directly to the cloud and into the stated application server.
And challenge 2, work environment complex, trying to manage Node.js and .NET in one project were massive. We solved it by splitting them into a repository with complete isolate Docker files and deployment pipelines. A solution, I split them into independent GitHub repository, each with unique Docker files and isolate GitHub Actions CI/CD pipelines for automatic deployment.
And our final struggle was the data bloat from the dead links. That's when the expired file and that link could accumulate and lead to offense or strange cloud asset. And so our solution for that we engineered the file cleanup service, the backend to perform periodic sweep, purging both the PostgreSQL metadata and the cardinal asset simultaneously. And moving on to after the slide, we move on to the live app demo, which I